To the fourth day and concluding day of the WINS workshop. And first presenter of the day, Professor Ajay B Harish, a research associate of NMCAD Lab for 18 years. He is currently a faculty member in the Mechanical and Aeronautical Division at the University of Manchester, UK. Before his PDF at UC Berkeley, he obtained his PhD from Gottfried Leibniz University, Hanover, Masters from Caltech, and Bachelor's from NITK, Surat. His research encompasses computational modeling, fluid structure interaction, and advanced materials. Now he is also working on neural networks and deep learning work. Thank you. Please start the presentations.
Yeah, thank you so much for the kind introduction. Let me just try to. Okay, let's see something. Okay, I hope the screen is visible correctly. Okay, yeah. Thank you. Okay, thank you very much, Professor Haru Sampal, for the kind introduction, and also I didn't get the name of the student who introduced me. Thank you so much, and thank you very much for the invitation. Today I'll be talking a little bit about some of the work that we are doing in regard to concurrent multiscale modeling of textiles. So it should probably be textiles, not textile composites, but later on extending it into the regime of textile composites. Hello? And so on. Yeah, sorry. Yeah.
Your presentation is not visible. Your screen is getting shared, but not the presentation. Yeah.
Okay, let me just try again.
You can see multiple windows there.
Yeah, sorry, I have 3 screens. I'm just trying to.
I think you're probably sharing the screen instead of window.
Right, yeah. Can you see it now?
Yeah. Now it is.
Okay, thanks. Sorry about that. Yeah, so I'll be talking about some ideas of multi-scale modeling of textiles that we have been doing and kind of later extending it on to textile composites. Just to give you an idea, I just want to give an idea of what we are doing in my lab, and the lab members are primarily doing the work, and some of the applications of numerical methods. And one of the things that I want to kind of, let's say, pitch in is some of the ideas of contact mechanics that we have been working on. And also one of the students at NMCAD Lab, Aditya, I think he already presented hopefully earlier in the week. And he would probably also be, this would also be going into some of the work that he has been, he'll be doing in the next few months, I would hope. Yeah. Okay, so what do I primarily do? My primary goal is to develop numerical method. That's kind of, let's say, the goal of the lab is to look at different types of numerical methods and see what kind of applications they can be applied into, and eventually release them as like open source research tools that can be used to model some of these phenomena. So that's where we are looking at. So I look at a range of methods like finite element method, finite volume, material point method recently, and so on. And recently, we've also been doing SPH, and of course, WAM has been a big part of some of the work that I've been doing. Just to summarize some of the work that I've been doing, some areas recently that we started was in biomedical on the right side. When I was at UC Berkeley, I started working on natural hazards like tsunamis, storm surges, inland flooding, and looking at fluid structure interaction in these problems. Then also on the left side, there are more traditional problems like textiles and composites. And for example, my PhD work was looking at tire rubber and metamaterials and so on in a way. Right? So so these are some of the lab members currently who've been working with me. So those in green are somebody I'm co-advising. So there's also another advisor involved with them. We're working on a range of problems from biomedical to looking at fluid structure interaction in the brain, and also like aerodynamics and deep learning and composites and textiles as well in a way to go ahead. Some of the projects that we are running on, just to give you a flavor of what's been done, is like one of the things that I started was looking at my PhD was to look at tribology and emissions. If you look at it, we have a lot of norms regard to the exhaust emissions that are coming out from the tailpipe. But when we are looking at a non-exhaust emission, which is essentially brake wear, tire wear, uh, or there's literally no emission norms in there. So we don't really have any kind of a measure of or control of what types of materials are used and how these are determined. So this was a project that was funded by Continental Tires in Hanover in Germany, where we wanted to build multi-scale modeling to look at how tires wear and how do things change at the microstructural level, where you're considering them as particulate composites and cracks growing through particulate composites, and eventually what would be these particle sizes. One of the biggest discussions that has been in the community has been do these produce very small fine particles smaller than 10 nanometers or less than 2 microns, and in that case they're a significant health hazard, and how do we improve that in a way. So that was one of the motivations for these for this investigations that we did as a part of my PhD. One of the recent projects that was funded through a collaboration with A-Star in Singapore was to look at multi-scale modeling of materials, but then more look at fluid structure interaction and to see how we can build smart textiles in here for various kinds of applications, ranging from sports to several other applications, like for example, like defense and so on in a way. And so we wanted to look at these multi-scale modeling of textiles and see how these uncertainties would grow from the lowest micro scale all the way to the like the fluid structure interaction of these structures as well. Another project that's been slightly inactive at the moment, but then that was started, was to look at like natural hazards. Like this is like a completely different scale of problem where we are looking at, let's say, a tsunami wave that is coming in and how it affects the structure in a way. But the physics of the problems is slightly different, but then at the end of the day, the same numerical tools of solids and solid mechanics and fluid mechanics is applied here as well. For example, here we could have like a building of interest, like in a 2010 Tohoku tsunami that happened. This was like a nuclear reactor. Or, for example, this could be like a storm surge where there's like, for example, oil rig or something in the middle of the ocean, and how the waves and wind would affect the structural behavior and, let's say, cause damage and these aspects. Look at the uncertainties in some of these hazard events that almost are very unpredictable in a way. And how do we design for these kind of events and so on. A more recent one that's been we are looking at is to look at like stroke and deep learning, looking at to help clinicians, especially clinicians who would not be able to run finite element and CFD simulations. So the idea was how do we build these things into like a AI architecture and use machine learning in order for them to be able to let's say have a risk assessment in a way. So give them some CFD results and finite element results, more let's say concise package that they can work with and they can look at. So there's funding from Translate for Manchester that primarily looks at taking lab applications into like a more clinical into the clinical area. So we're in a presently in a stage 1. So if we go into stage 4, then should be able to kind of translate these things into a like actual clinical application and deploy them with the hospital in a way. Latest one that we started was to look at like fluid structure interaction in the brain. This was more interesting, very interesting for me at some point, was because the flow in the brain is very laminar, and I have no experience of turbulence. So, for example, in aorta, it's a lot more turbulence, but in the brain, it's much more laminar in a way. And we can't really look at how much blood is there in each of the single capillaries and veins and so on. Only the larger arteries are something that we can measure with something like an MRI, but we can measure the oxygen levels and water content in different parts of the brain, and using that to decipher what is the blood content in different parts of the brain, how is the brain getting these things, and can we send more blood into certain parts of the brain to, let's say, allow the tissue to heal and look at it as a medicine for neurogenerative disorders. So this is a very latest one that we started out, and we have luckily we got 3 PhD students to start working on this area as well. And thank you. So before we go into like let's say textiles, I want to just give you a flavor of it and try to then introduce some of the contact work, contact mechanics work, and oops. Okay. So this is like let's say a micro scale modeling of the textile that we are looking at, where we are. So most often at the micro scale, people assume shell models and so on, or even solid models. But what we want to do different is to look at our microstructure as comprised of beams in a way. So each of these are beam elements, and we are looking at the contact between these beams as a yarn. And at the moment, the work that's being done is assuming that it's a circular cross section. So one of the student at NMCAD Lab would be looking at different kinds of cross sectional areas, well, looking at these things as strip beams and so on. We're using WAM, which would be a much more efficient solution than what I'm showing you here with the standard finite element. So a big focus of my work has been on contact mechanics, particularly starting from as the most simplest problem is what we know as a flying spaghetti problem. So if we take a spaghetti and just drop it, so how would the spaghetti kind of like have self contact and several other aspects in a way. Uh, And so then for example, a part of my PhD, we were also working on like looking at 3D contact, where you have like contact on a rough surface, and especially for tribology and looking at how tires interact on a let's say on a road. Then we want to look at these kind of problems. So the core strength of the group has been looking at contact mechanics and developing a lot of contact mechanics algorithms and using them in various applications. Like for example, 3D. So if you can look at, if you see that the surface is reasonably very rough, which means it's extremely convex in nature, and you have lots of convex and concave surfaces, and the hard part is to kind of build a robust algorithm that works across these kind of different contact settings, or to look at very flexible beams in a way. So here these are rigid cross sections, but of course with WAM we should be able to do a much better, more efficient job to look at very soft issues. So this was basically like something that we were just thinking of in a evening to see if we can use it for some particular purpose. We just were trying to run some applications, but no particular application in mind when we ran these problems. So okay, so let's try to take a step back here and try to see how do we formulate these things. So when I went into Caltech, so for my masters, that's where I learned most of my continuum mechanics, apart from what I learned at the NMCAD lab. A big part of it was like, okay, we did courses on solid mechanics, fluid mechanics. It was never applied, and one of the things that stuck with me was like, like everything is essentially, bottom line is continuum mechanics in a way, right? Everything, as long as you can provide a continuum description and we don't have a break of that, then the general continuum mechanics ideas can be used irrespective of whether we are modeling a solid, whether we are modeling a fluid, as long as we are understanding the physics of what we are modeling in there, right? So just to, before we put in some formulations in there, I just want to introduce some basic notations. And so we generally, like, as you know, we would always have like a reference configuration, and we are looking at a deformed configuration. And most of the formulations in solid mechanics has been based on, let's say, a deformation gradient that looks at the difference between these two particular configurations. So one of the things with flexible body contact is that the formulation is very similar to plasticity. So for example, a very simple way of thinking about it is if we have two balloons, and if these two balloons are coming into contact with each other, then essentially, let's say we can initially assume on a, let's say on a computation framework that they're not in contact. It's a nonlinear problem. Solve assuming they're not in contact, check if they're in contact. Then again solve if they're not in contact, check if they're in contact. If they're not in contact, everything is nice. Now, if they're if generally, like, we'll almost never get a situation where they're exactly in contact. Most likely what's going to happen is that these two bodies are going to, let's say, in our, let's say, trial step, like in plasticity, we take a trial step assuming that it's not yielding. Here as well, we solve it assuming that there's no contact. And then we check if there's a contact and then do some form of a correction in there, just like similar to radial return algorithm or other algorithms that are used in plasticity. So we assume that, for example, the most simplest thing that's used is like a gap function. And if we are, let's say, if you're looking at a rigid body, this is very easy to do because the rigid body, let's say if you have two spherical bodies, then the radius of them is constant. And you can easily say that, let's say the distance should be greater than the sum of the two radii. But the problem comes in flexible body contact, because let's assume that they have some kinetic energy and they're moving towards each other. And once they come into contact, they're going to elastically deform as well. And there can also be plastic deformation. They're going to deform. So some part of this kinetic energy also goes into the deforming these two bodies. It's not and we need to account for what are these deformations. If they're in rigid body contact, there's basically just like crashing across each other, and there is not going to be any deformation between the two bodies itself. So that makes flexible body contact much more complicated and let's say less robust when we are trying to solve it with numerical methods. So one of the most fundamental things that you would look at when once you open a contact mechanics textbook is what's known as a non-penetration condition. So you always have, let's say, we always think of idea as one body as a master body and one body as a slave body. Of course, there's been a very recent paper from my doctoral advisor and from a very good friend of mine who started, let's say, wrote a new paper saying that why don't we consider both of them as a master body instead of saying one is a master and the slave is going to be following that. So generally we have a master body and a slave body, and we are going to project every slave body onto the master body just to check that the slave body does not penetrate with the master body, right? So you take every point on the slave body, project it onto the master body and find the normal distance between them. And most of this is always done in the current configuration rather than in the reference configuration, because most of the contact formulation is generally thought about as like what's happening at the current state of deformation rather than in a reference formulation. But it can always be formulated in a reference formulation, just that it would probably be a little more complex than in the current configuration. Okay, so in the current configuration, we have two bodies. Let's say we have a slave body, we have a master body. And our goal is to make sure that these two bodies are not interpenetrating, right? So just to go back in there and give a thought again, like, so we have two bodies we are solving as a finite element, let's say in any kind of numerical method, and we want to assume that these two bodies are not in contact. So we kind of always assume that they're not in contact, make the next iteration, check if they're in contact. Now they're not in contact, make the next iteration, we check if they're in contact. You see that there's an interpenetration. Physically, two bodies cannot interpenetrate. So ideally, you want to move these two bodies a little bit further away such that the total energy is distributed to also accounting for their deformations. But then, for example, let's say if it was a rigid body, it would be very easy. You can just move them apart so that they're just in contact. But now with the elastic body, now these things are also going to deform a little bit. So there will be some kind of a deformation in the body, which also needs to be accounted for, right? So that's where our minimum distance problem comes into picture, that you define one as a master and one as a slave, and you don't want to do a n square algorithm. What do I mean by n square is like you don't want to take every point on the slave body, check with the master, and similarly you don't want to take every point on the master and check with the slave. It becomes a computationally very expensive. So you basically just take the slave body and check with some regions of the master in a way, right? So make it more computationally more efficient. So there are three conditions that we look at when we are looking at the check. So, and this comprises the entire idea of contact mechanics. Let's say so the entire contact mechanics is summarized in this slide. So either you have the two bodies are very far away. So then there's no contact, no complication. Life is very nice. You can go home at 5 p.m. Right. So the problem is let's say if they're exactly in contact, which is almost never going to happen in a numerical framework because you're using floating point numbers, which would essentially mean that what is zero, right? So if a minus b is zero, so when do you say it is zero? It's when it's 10 power minus 2, minus 4, minus 8, minus 16. So you're almost never, I've never seen a case where you exactly get a, let's say, intermediate state where they're exactly in contact. So it's like a very, very, like, let's say less than 0.0001% chance you might end up there. But more likely, you are going to end up with a case where you have some form of unphysical penetration between the two bodies, and then you want to, stay. You'll have to end up staying till midnight trying to solve the contact problem, right? Okay. Let's try to see how to impose this contact constraint in a finite element framework. But the same idea also holds true for WAM or any other framework itself, where you're trying to do energy minimization. So So with regard to a finite element, what we generally do is, okay, so this is essentially our weak form that we have in our finite element. We have the traction forces, we have the body forces, and we have something from our internal energy. So in general, I would say this is some form of an internal energy, and this is some form of an external energy, let's just say. So this is the work done by the body forces under traction, surface tractions, and this is just energy stored in the body. So what we are going to add is we are going to add an additional term, which is a function of Gn and Gt. So when I mean Gn, I mean the normal contact, normal distance between the two bodies. And when I say GT, it is the tangential distance between the two bodies. So we can assume that the two bodies are not just moving normal to each other, but they can also be moving tangential to each other. Like we saw earlier in the flying spaghetti problem, as the spaghetti made a normal contact, it also started sliding along the surface and so on. Right. So and then once it touched the tip, then again it started to rotate and so on. So and also on the 3D surface, we saw it was moving on the surface. So it's not just the normal contact, but there can also be frictional contact. Right. So we are saying that we add some energy in there that depends on this Gn and Gt. And eventually what we want to do is we want to take all of these things and minimize it to zero in a way. So we want to take the entire term and minimize to zero. The most nicest thing would be if this term goes to zero, then essentially we can easily minimize our problem. But then that term might not necessarily always go to zero in a very easy manner, and so that is our reason why we want to think of how to, let's say, write these energy forms. So there are several methods. So people said that, okay, so now we are adding a constraint. So now we go into the idea of holonomic versus non-holonomic constraints. And most of the times you're writing it in a holonomic form where you're not writing in terms of velocity, but you're writing in terms of displacements. So there are several things that people have done so far, especially in applied mathematics and mathematics, looking at how to apply a constraint, right? So essentially, you transform your problem of a contact into a problem of constraint, applying a constraint in there. So there are several methods like penalty method, Lagrange method, augmented Lagrange method, and each of them have their own pros and cons as to why you should use one method over the other in a way. Right. So for example, if I'm just going to write the normal part, so yeah, I've written a tangent. Sorry, yeah. So if we are looking at Lagrange multiplier method, we are saying, let's start with the penalty method. So with the penalty method, we are saying that we are going to assume some penalty parameter, let's say Ct and Cn. These are some user-defined parameters, right? So we always like when we write material models or when we write these models, we always like to put these parameters because we can always fit with these parameters, right? So I saw a paper some time ago when I was working on my PhD. This was very earlier years of my PhD, where they had about 27 parameters. So we were like, okay, you can fit an elephant with 27 parameters, literally, right? So we always like to add parameters in there because that makes our life more easier. We can fit things with it and so on. So people said, like, okay, we can add some penalty parameter in there, and which is like a normal penalty parameter and a tangential penalty parameter, right? So we are seeing Cn and Ct. And this is basically writing, let's say, our tractions as like Cn into G, which is nothing but a gap function, and Cn into Gn, which is nothing but a gap function in a normal direction. So I'll come to the tangential direction in a minute, because normal direction is always nice to think about. Tangential direction is always a little more complicated. So let's say there's some tangential movement between the bodies. We will think about what that is in a moment. Don't worry about what this n+1 is. We'll come back to that again in a moment, right? So let's say, for example, we have some gap function in normal direction. There's some movement in a tangential direction, and we have defined some parameters that allow me to really play around with it. And now I am going to write it in a formulation. So what I'm doing here is essentially nothing but, let's say, the whole idea here. So this is essentially nothing but like a equivalent to your pressure. So your normal pressure, and there's no real tangential pressure, but think of it something like a Newton per meter square, and or meter cube, and essentially, meter square, and then essentially you're integrating that over the area. So if you're Newton per meter square and integrating over the area, you're getting some form of a force. Now this force into our, let's say, virtual displacement in the normal and tangential directions are giving us the work done if I have to move the body by a small amount delta Gn in the normal direction or delta Gt in the tangential direction, right? So Lagrange method is very much similar. So you have instead of a user-defined parameter like Cn or Ct, you say, what if I don't know this pressure a priori? So by defining a Cn or Ct, you're saying the pressure should be approximately about this magnitude. But in Lagrange multiplier method, you're saying that I don't know this, and it becomes a part of your unknowns. So on your vector of unknowns are not just displacements, but displacements and Lagrange multipliers. But then the disadvantage of this is that you end up with diagonals of zeros, which destroys all the nice properties that you can have with your stiffness matrix. So, and additionally, Lagrange multipliers have a lot of oscillations in the zone of contact. So when you're very near to exactly to the contact, then Lagrange multipliers have a lot of oscillation. But then once they oscillate, you allow them to oscillate, the constraint is, let's say, satisfied to a very high degree of freedom. So so it satisfies it very well. But with regard to penalty, there's no oscillations, but then you would have some bit of an interpenetration, right? So depending on how big your parameters Cn and Ct are, you can control the amount of interpenetration. So can you live with a 1% loss in accuracy? Can you live with a 0.5% loss in accuracy? So that's kind of where penalty approach kind of approximated so that you have a faster convergence. So augmented Lagrange multiplier, if you look at it, you have both the Lagrange multipliers and you have the penalty parameters in there to take the advantage of both the methods to lead to a faster convergence, but to a better fit in your constraints, in a way, right? So this is the entire idea of contact mechanics. How do we first thing is like we want to add a constraint in there, and we are defining this constraint in terms of some amount of energy or like variation of energy, and how much of this. And second thing that comes in is where do we add these things, right? So there's a weak form. So now how do we put this into a discrete form? But before we go in there, I said that we want to look at also our tangential thing. So when it comes to tangential state, it becomes a little more complicated. The same idea also applies to like as problems like earthquake, where you're looking at friction between the two plates of the earth in a way. For example, there you're looking at stick state and a slip state. So it is a stick state. So the two bodies, there's no relative motion between the two bodies. The two bodies can move, but then there's no relative motion between them. Right? For example, think of two balloons. These two balloons are coming into contact with each other. There's a tangential motion, but then both of them are moving. At that particular point, there's no relative motion. So for example, at that point, you can say there's a stick state. But there can be a point in the neighborhood where there can be slip state. That means that there's relative motion between the two bodies. So we need to be very careful here. For example, in our work, most of the time at very low speeds, we are very happy to, at least especially in textiles, we are very happy to consider that the friction is somewhat simple Coulomb's law can be used. Of course, that's something to think about again. But then we are using a standard Coulomb's law where you're saying, let's say the tangential force in a way lambda t minus mu is the frictional coefficient. Lambda n represents somewhat your normal pressure is less than or equal to 0. So that's, let's say, something like our yield function. And if this is less than 0, then gt dot, or the rate of tangential motion, is essentially 0. So there's no relative motion between the bodies. And if it is not the case, then that means the tangential force from friction is much higher than your, let's say, mu into normal force, which means there's going to be some relative motion between the two bodies. So depending on that, we define our tractional force in a way. So for example, here you can see gt dot is 0. That means that the traction force is sliding traction is 0 in the case of stick state. In a slip state, that is non-zero, right? So that automatically kind of then goes back into our previous slide here, where we have where we are imposing our variation of our energy in terms of Lagrange multipliers or penalty parameter, and that's where it contributes. The traction kind of goes into the contribution here, right? So we have the traction parameter. Okay, so now there were two things. So one was, where is the body in contact? We have not yet solved that. So once we know that 2 points are in contact in the body, we know how to impose our let's say our constraint. So like we started saying that two bodies coming into contact. Now let's say we discretize the two bodies do with points, and we are looking for point to point to see, okay, which point is coming into contact. And now based if they are in contact, then we are going to impose some constraint. If they're not in contact, at that point, we don't have to impose a constraint. But now how do we put this into a discrete form? Essentially, we want to solve a matrix equation. We have this partial differential equation that we said, or that we started out with. Then we converted that into a weak form or an integral form, from where we are putting it into a matrix form, which we can solve for. So our whole goal of many of the numerical methods is to take this kind of integral or differential form and put them into some form of a matrix form. So what we generally would do is we divide our matrix into elastic part, and there can also be other nonlinear parts coming from material nonlinearity or geometric nonlinearity in terms of finite element, and then you also add a contact part into that. So with regard to the WAM, essentially we would be doing something very similar, and we get a matrix equation that we can solve for displacements, and use a vector of unknowns here. If it was if you're using only a Lagrange, only a penalty method, then this would be only displacement. If you use Lagrange multiplier method, then you also have those additional constraints coming in there. And our contact stiffness matrix is nothing but the stiffness matrix that we get from our additional form that we are adding as a part of CC, right? So CC is our additional constraint that we are adding, and or variation of our energy that we are adding, and from there we get our contact stiffness matrix, right? Okay. So now the second question that comes in, first thing is we know how to impose a constraint. Second thing is we said if the bodies are in contact, then we impose a constraint, but we don't know where they are in contact. So that is where the contact search strategies come into picture. So there are two things. Primarily, one is how do we put the constraint? Let's say point to point. Let's say simply to think about it, but then point to point might not always be accurate, and it might be very cumbersome to look at. So then, for example, we want to look at different ways of imposing these constraints, right? So that's where the contact search strategies come into picture. So some of the very common ones are like looking at a node to surface or a node to analytical surface. So node to analytical surface was very interesting for us when we were looking at the problem with the road, because we, as a mechanical engineer, or we are not concerned about what's happening to the road. But probably as a civil engineer might be more interested in how the road surface itself is degrading in a way, right? So, but then as a mechanical engineer, we would say, okay, the road has some particular surface roughness, and then we assume that is analytical surface that's not changing at all, which is not really true. But then such approximations are something that we need sometimes in order to, let's say, make our complex problems more solvable in a way. Another other thing is like looking at node to surface strategy, where you're taking a slave node and projecting onto a master segment. So for example, if you had like a, let's say 2D problem, then you basically have like a line on your master surface. So each of your element is a line, and then you're taking every node and projecting onto this particular line and seeing what's the distance between them. Alternatively, one can look at a surface to surface strategy, where you're taking one surface and kind of projecting them onto a second surface and trying to find out what is the overlap between these two particular surfaces. So this kind of makes it so, especially when you have large, let's say, sliding, then node to surface strategies could fail quite a bit. So that's the reason why we want to look at surface to surface, and also we want to look at. And another problem with surface to standard surface to surface is that it would probably, yeah, surface to surface would essentially be that it could also happen that when you have large rotations, let's say if your two bodies rotating against each other, then the surface to surface strategies will fail. So generally and second thing is your mesh densities across the two surfaces are different, then surface to surface strategies fail. Right? So there's like, to some extent, there's like a bit of tweaking to find the right recipe in a way. So one of the things that recently developed was also worked on my PhD was to look at mortar contact, where we can look at mesh densities of different very largely different mesh densities on the two sides. So what you do is you take a projection plane and you project everything onto this particular plane and divide the, let's say, whatever is intersecting into pellets, and use that as your integration points to build your stiffness matrix, right? So And so it's again like looking at surface to surface strategy, where you're looking at you can probably also look at take each integration points from your slave surface and also project them to the master surface. So you don't, and so these are the point, and then you can again like look at the let's say the intersection between these 2 points. So there's also integration point to surface in a way. So this is what we do with a mortar surface. We can take any random plane and project everything to that particular plane, and that's where all the projection is done and the linearization is done in order to look at how to find the overlap between the two surfaces. So once we know what the overlap is, then we are able to use our variation form and do a linearization of this form. And most often these are the terms that are very hard to calculate. Some of the terms are basically assumed to be zero and approximations are made. And that is the reason that contact becomes much more harder to solve, particularly because so some of these linearizations are very harder to calculate by hand in a way, or let's say to derive them. Yeah, in the recently, we have been using Mathematica to do some of these or derivatives and even, let's say, generate codes from some of them in a way. So that becomes a tricky thing. So when you start to neglect terms, then your stiffness matrix is no longer consistent, and the convergence starts to slow down. So if a residual is not correct, then we'll never get a convergence. But then if a residual is correct, which is more easier to calculate, but our tangent stiffness is, let's say, inaccurate, then we would end up with a very slow convergence, though we might get a convergence, most likely possible to get a convergence. Right. So the thing that comes down is like, how does it differ for beam to beam? So some of the things that we started with a preliminary thing, we said that we assume that we have a circular cross section, and we assume that the cross section itself is not deforming, which is not essentially right. But for the application, we said probably, okay, let's start with something more simpler to start with, and then we can use that to build on that. So then we assume that we can get a, like you can easily calculate, let's say all of these trajectories analytically, and we should be able to calculate. Okay, I don't know why the image is distorted, but we should be able to calculate all the dissipative force and all the things, particularly with regard to like a beam modeling. So what's more interesting is to look at some of these results before we go into results for multi-scale modeling. So I would like to show. Oops. Okay. Yeah, so this is a let's say a simulation of some of the simulations that we did with the contact algorithm, and I'm not very sure why the rest of the slide blacked out. Okay, let's see if it comes back right. Okay. So you can see, so this is a very simple case where you have like a line where you have like a surface contact between the two beams where they're perpendicular to each other, and this surface contact is reasonably smooth. So there's a very simple case to start with, where if to look at the benchmarking example where you're like kind of like applying a load and the sliding of a second beam along with it. So there's a constant surface contact. So that's kind of what we see when we look at is the arrow. Once the contact is established, pretty much the contact force is reasonably constant. It's not constant, but then reasonably constant to some extent. So a more interesting problem is to look at, for example, when we have like jumps. So here, for example, the direction of contact suddenly changes every time you have like a kink in there. So as you can see also on the right side, what we can see here is the gap. So for example, the blue color is the FX and red color is the FY and green is the FZ. So FZ is FZ is into the plane, and that is a reasonably very negligible compared to the FX and FY. And as it rotates, you can see that the FX and FY both change in both not just the direction, but also both there's a change in magnitude and the direction, and particularly jumps near the kinks, which are really more complicated to capture, particularly when there's a sudden change in, here there's a reasonably smooth change in the, let's say in the normal vector, I would say. So that since we are taking these derivatives, any kind of a change in the normal vector would need to be saying that, okay, well, if there's a derivative, then it's not any more continuous, then how do we take the derivative? That becomes the complication here to look at it. A very similar case is to look at contact between two beams where we have these sudden changes in still smooth change, reasonably smooth changes, but still changes in the, let's say, in the direction and the magnitude as well. Uh, so for example, here again, we can see the fx is in blue, fy is in red, and fz is in green. So there's changes happening. So z direction is the upward direction where we are moving, and x is in the direction of the motion, and y is into the plane here in this example. Anyway. So there's both changes in direction and magnitude, though still reasonably smooth. Again, but then the normal vector changes at each of these points, which need to be carefully accounted for. A more interesting contact is to look at line contact when we have a parallel contact, and to look at twisting between the two beams. So I am showing some of these things because all of these things essentially form the ingredients of what we do in a multi-scale model in a way. So essentially, as you saw here, wait, let me go back. The arrows basically are showing somewhat a magnitude of the force, and as the beams come into more contact, the magnitude of the force reasonably increases quite a bit as you start twisting. And these are interesting to look at some of the textile composite, because each of these textiles are not individual beam, but then they already have like a bunch of beams that are twisted together. So that's kind of what we want to look at in the next step. So similar thing is like to look at a parallel contact where you have contact between two, let's say, two beams. All of these are 3D examples, even though I'm showing the cross section here, it's still a 3D example. And another parallel case is to look at, let's say, when you have a beam to beam contact, and the most simplest case to look at how to handle these parallel contacts and so on. So most of these things, again, like for example, has a, like so far we saw was always it has a surface to surface or a line contact or a surface contact that was always constant. But I think the more interesting thing is in the rotating beams here. For example, if you start, we have a line contact, and as we rotate, we have a surface contact, and then as we rotate, we change to a line contact in a way. So that's you can see that there's a sudden change at that point, and then as yeah. Right. So, for example, you have a contact along a line rather than contact along two surfaces, and then again, as it rotates, it again changes back to a surface contact, and that kind of completely changes the contact regime that you are looking at. So the idea would be to see how we can smoothly handle these kind of changes that are happening in both the normal vector and in the contact area, and that just to show again. So yeah, so this is the. Yeah, it's just to play the video again. So now you see that it's basically two patches of surfaces, and as it rotates, it basically becomes a line contact between two cylinders, and then again it changes into a surface contact. So all of these arrows are essentially depicting some form of a force magnitude that we experience between the two beams, in normal forces in between the two beams. So the idea was like, okay, so now we have like a framework that can work with the two beams. So can we put them all together to look at our textile composites? So here we assume that some kind of a nonlinear interface law between them to look at the friction itself, and also the normal behavior. And we wanted to model these things. But then our last, I'll probably come to the last couple of slides and want to leave some time for discussion, is to look at how do we do a multi-scale modeling. So the idea was very interesting for me, primarily because most of the work that's been done at let's say, some kind of multi-scale modeling, either does some kind of a curve fitting at the micro scale, runs some micro scale simulation, does a curve fitting. There's a very recent paper where they use a Gaussian process regression. I mean, of course, with all the machine learning, everybody's crazy about doing neural networks. I'm not yet convinced on that is the right approach for this problem, but one would like to run a lot of simulations, get some results, train some neural network, and now I do a multi-scale modeling, right? So I also did the crazy stuff with the neural network, but then that's the reason I say it's probably not a convincing solution. But then here we said, since we have a beam-to-beam contact between the things, it can be much faster, right? So we don't have to, let's say, solving a 3D solid problem takes more time. But then if you have just a beam, then this is much faster to solve it in terms of computational times. So what we started out doing was, let's say if you have a macro structure, can we, let's say, go at every integration point? A very simple FE square approach. Take the deformation gradient at that point, apply it on your microstructural RVE, solve the problem, get the P-Kirchhoff, second P-Kirchhoff stress and the material stiffness from there, and give it back to the integration point at the macro scale. So, our biggest question was, how do we transfer this deformation gradient, which is somewhat like, let's say, a 3D representation, into the representation in our view at the micro scale? So what we said was, can we divide up our view into 4 different, let's say, deformation modes, let's say, at the micro scale. So we say, basically, let's say if we have, this is our, let me just take, okay. So if this is our actual deformation that we want to apply, can I divide it into deformation A plus B plus C plus D? So that was my idea in a way, to kind of decompose our deformations and say it's like a super, let's say if I have an alpha 1 here, so I have not added, so alpha 1 into delta U1 plus alpha 2 into delta U2 plus alpha 3 into delta U2. So there's these alphas here. So in a way, can I decompose them into 4 different deformations and superimpose them in a way? So I take my deformation gradient and separate them out into 4 different modes of deformation, and then put them all together to construct, let's say, displacement vector for me. So what we do is essentially we take the 4 sides of the view and apply a displacement on all the 4 sides of the view and solve our micro scale problem and get our, let's say, our material tangent and the stress components from there to put them back into the multi-scale framework. And our second question was, what represents an RVE size, right? So is a 2 by 2 does it represent an RVE size? Again, here it can become complicated if you're using a, let's say, a standard view versus a twill and unsymmetric, symmetric, and so on. But let's say if we start looking at different view patterns, view sizes, we were able to look at, there's something else on top of that, but yeah, look at like the different views and say that, okay, our 2 by 2 is already a reasonably representative volume element that we can look at. So just the last slide before we finish. So I want to leave with like these are like the force and effects and FY forces that we are getting out of the multi-scale models that we are looking at with regard to the, let's say, or both the micro scale results and the macro scale results, and let's feeding into our neural net, into our, like, let's say, our multi-scale framework. And let's say this is still a work in progress to some extent. So this is something that we are trying to finish up and write up as well at the moment. Thank you so much for all the kind attention, and I'm happy to answer any questions.
Thank you, Ajay. I really like the presentation, really engaging. I do have a question. When you were, I think it was in slide 21, when you were showing between the stick state and the slip state. If I remember correctly, there is let's say a friction coefficient for the static case, and then there is a different friction coefficient when you are already in the dynamic state. And it's not just 2 values, but rather a curve that, depending on the slip, it changes. Is that something that can be considered with these models?
Yeah, we can consider them with the model with the stick state and the slip state. Only thing that becomes complicated when we are putting it into the next formulation here. Where did I go? Yeah, so in the linearization for a stick and a stick state and a slip state, we would have another term that comes in because of the change in the friction coefficient. And generally, we try to avoid that by taking different friction coefficients. We just think of them as 2 separate different linearization and switch them between one and the other, rather than considering the additional, let's say, linearization that you need to do because of change in the coefficient itself in a way. So we can consider the 2, but most often we try to neglect that additional term that could have come into the tangent in a way. I mean, what you say is perfectly right. We need to account for that. But every additional term is a lot more complicated to, let's say, derive. So that's the reason some of these, like, you just switch them rather than kind of like assume the derivatives exist. And most of the times it kind of works in a way.
And then
Yeah. So what?
No, that.
Please go ahead. No, go ahead.
Yeah, this is more a curiosity because it's a question from a project that you showed in the introduction when you were considering the slip of the tires with the asphalt. Which type of road was considered? Because I mean, you can have asphalt, concrete, and nowadays when you add recycled rubber to it, the amount of like debris that comes from it is less, right? Is that something that was checked as well, or which material was?
So I mean, definitely we didn't think about doing the Indian roads at all. So of course it's so we wanted to eventually compare with like the gross wheel test experiments. So the gross wheel test experiments are like something like so we didn't even look at real conditions. So gross wheel test essentially has like a wheel that's rotating in the vertical direction, and then you have like the horizontal direction. So because of the vertical rotation, it causes the tire to rotate in the horizontal direction. You can also apply additional rotation to, let's say, add a little more force in there and things like that. So this is the project that we were working with Continental Tires in Germany, who have their headquarters in Hanover. So I mean, at least at that point of time, this was like, let's say, a few years ago, like the way they were doing was like, you let's say weigh the sample before you test it and weigh the sample after, right? So it's a very crude way of saying how much the tire has worn out. I mean, I understand why they are doing that, because the complete problem itself is very multi-physics. It involves temperature and so much of things that it's really hard to do an actual full mechanical calculation in there. So that's kind of the test that we had at the macro scale. And at the micro scale, we had additionally like scratch experiments I was doing with the nano indenter to see how we can kind of use a scratch test and see if we are able to replicate that at the micro scale. So we really didn't compare anything to the real conditions at all. So I think there's our results, like I don't think are a representative of the real condition. Essentially, what we were looking at is, let's say, if we are able to measure the particle sizes coming out of the gross wheel test, let's say, and if we are able to, let's say, sample them out by size and say, okay, we have this distribution, what is the kind of particle size that separates out when you have a crack growing in your microstructure and let's say separates out as a piece. So that was the limit of the finite element simulation that we were doing at that point, because once the particle separates out, then you need to treat it as a third body in a way. So we did like hundreds of simulations with the different microstructures with different, let's say, distributions and different particle sizes to see what is the variability of the, let's say, size that would separate out once the crack grows through this kind of a microstructure. Now there were a lot of questionable assumptions put in there. I'll be very honest, because crack growth in rubber itself is another completely different PhD in a way, completely just to look at it like, so why is crack separating out? And now people say that most of the cracks would go through the rubber, will not go through the filler. But we saw it, or like through the interface was most of the cracks, but then there were also some cracks, very few that could go through the filler as well. So we wanted to see how we can capture these things, and it does happen in a way. So like, what is the like? So we use the coercive law. So now, what are the properties of this coercive law? Again, like, we put in some assumptions in there. Like I said, like another set of numbers that are again very hard to estimate in a way. So we were very far away from any kind of realistic, let's say, ground truth predictions. We were very, let's say, grasping at last straws in a way to say, kind of like to even be able to see if we are able to match the experiment that's in a laboratory condition, controlled laboratory condition. I think that was the limit of what we were able to get to in that project.
Okay, thank you.
I mean, it's a very interesting problem. The problem is that it's not as fancy enough as many of the problems that say, who cares about how much tires wear out, right? So kind of like, it's like, except the tire companies, nobody really cares about it to some extent. I mean, there are some people who care, but so the amount of, either you have to get funding from the, like, tire companies, and then there's always a hidden agenda in them, what they would fund. They wouldn't want anything that kind of negatively affects their bottom line, right? And if you go to a standard funding agency, it's very hard to get funding from them, because this is not something that they can say that, oh, we've funded this thing and we revolutionized tires. I mean, uh, doesn't really have the vibe of saying that, oh, we kind of solved cancer or something like that. So kind of the funding for that kind of work is very limited in a way. So it's hard problem to do, interesting problem, lots of nice mechanics, but then there's no money to do it. You know?
Thank you.
Thanks a lot for the presentation. And contact is a very complex problem, so it's really a lot of work here. But I'm curious, what is the objective? At one point that you model the contact is mainly to investigate then the deformation inside the textile that deform the different fiber, or there is because you show some example very complicated from the contact point of view, but a little bit the circular, polygonal one that not so related to textile. So what's a little bit curiosity.
Okay, so the idea there was essentially to kind of, let's say, to see if we can, you mean this one?
Yeah.
Okay.
So this is an application for the textile, or this was really to test the content? Because from the content point of view, it's very complex.
Right. So this was basically to test the robustness of our contact algorithm, primarily because the normal is changing, and that every time the normal changes, then you need to take the variation of that and linearize that. And most of the algorithm, most of the things, like even commercial software, they kind of like eliminate this thing. They kind of put some stabilization in there to make everything work. But then if you have very large changes in the normal, then especially like, let's say, kinks, then the contact algorithms stop working in a way. So that's kind of where it fails. So we were just trying to test how robust is our algorithm, what can we do with it, how can we push the limits of it. And basically we want to see, for example, let's say if there are two textiles, especially one of the things that I want to, the student at NMCAD Lab would be doing is if you have two strip kind of a beams. I mean, this was a very nice thing that we took here. We had circular beams, which was very nice because as you rotate, the contact is always there. If you have a strip beam, then as it changes, it kind of changes from like a surface contact to a line contact, and there can also be some kind of like, let's say loss of contact as well at certain places, depending on if they're not symmetric and so on. So we wanted to here test the robustness of the contact itself, and then see if we can apply to more cross sections that are not circular in a way. I mean, so the idea was that you should at least first work for the circular thing before we start to apply for the other things. So that's the reason for looking at the robust. How robust is it, and what can we do with it? You know? Yeah. So eventually now we want to look at like let's say views with different more complicated textiles and see how we can use it. For example, not just like so at the moment it's just mechanical, but then can we add in more multifunctionality into it? Let's say not just like piezoelectrics, but then like various other things like magnetics and electrics, and see how we can control the properties of the textile itself, and how it would react in different environments and so on in a way. For example, can we have like can we 3D print these things that can like absorb water and so on?
But are you planning to consider, so for example, the deformation of the textile, that one, for example, the textile extended, the contact changes and so on? So in the,
Yeah. So we are benchmarking them for like simple things like uniaxial, biaxial extensions that are primarily also available, like because that's what we can do in experiments in a way. So we have some experimental collaborators who have done that, and we were kind of comparing that with that, and then look at a more complicated case like a scissoring case in a way to look at that would be, I think, the most grueling one, most difficult one to kind of be able to predict. And if you're able to do that, then I think then we have something that reasonably works very well to work with.
Really complex presentation, complex topic. The content is really difficult topic. Yeah.
Yeah,
go ahead. Please go ahead.
No, nothing. Please go ahead.
Yeah. So thanks once again for waking up so early and presenting this. See, typically most people, irrespective of whether it's a seminar, a conference, or a workshop, they design their presentations in a very similar way. But I think this was one of the befitting presentation designs for a workshop, because contact, as both of them have said, is a very complicated topic. And you being an expert on it and having applied it to many different problems, could have just focused on the research area. But I think you took into account the kind of varied audience that we have here, to start from the basics of contact, have the building blocks of beam contact in different directions, and then essentially putting it into the research problem. So I think that makes us learn a lot. So wherever we are from, whatever our background is, there is some kind of a takeaway for us, and that's what a typical workshop presentation should be. And yours put together with Aditya's presentation a couple of days back, it's a great combination because you've been mentoring him as well. And so a lot of questions which were kind of still unanswered got answered over here, in the sense that these two worked in a very complementary way. So thanks once again for your excellent talk.
Thank you, Professor. Thank you very much for a nice invitation.
Yeah. Right. One application I could probably suggest, maybe you already have given a thought to it because you work on tires. But even in regular modeling, because I've been in discussion with Airbus for a long period of time, they have a lot of issues with process modeling. How the temperature, pressure cycles vary with time, and how they affect the end product in terms of the especially the fiber orientations. So now you're doing a textile, but textile composite is another end, because the matrix is already rigidized almost. But the process of manufacturing, especially in the autoclave, there it is still in a semi-solid state, and because you have a lot of expertise in fluids and fluid related areas as well, I think you are in the best possible way to look at this solid fluid interaction that is happening, because the way you built up your problem, it's kind of modular. As you presented, I could see that. So I think if then this becomes a building block to put into like a semi-solid and see how things change with that. I think it'll be really beautiful, because most people tend to ignore contact, one because it's complicated, other if there's an a priori assumption that it may not be that significant impact on the overall behavior of the structure.
Yeah. Thank you, Professor. Yeah, that's a very nice comment. Actually, just yesterday we finalized the project on the same directions, where we are combining finite element and with SPH. So to look at SPH as like to look at like the mixing with the flow and the viscous flows. I mean, SPH, there are some things that are questionable with SPH. I won't say no. But then like with very low viscous flows, and if you have free surface, then it does a reasonably accurate job. So we want to look at that for the mixing of the matrix when it's in a semi-solid, let's say more liquidy state, and then look at the rest of the fibers and the other composite elements as like a solid. And then eventually once it's in a particular shape, then look at like how the let's say the cooling happens, and how various changes and residual stresses develop in a structure. So to kind of combine a finite element with SPH, and to kind of like look at the overall manufacturing process of the composite itself. So, and that's kind of something that we just finalized yesterday, and we have a very good student as well who is doing his bachelor project with me. So we have already got a scholarship for him that hopefully he'll start in late July or early August, and on his PhD on the same topic. And it will be very interesting to look at how we can extend that and build on that and see other interfaces with it as well.
Quite a lot of exciting, interesting things. To add to that, the proposal that we have submitted between IISc and University of Manchester for hydrogen storage, I think that will also be very interesting, and a lot of learning that we have got from the Delft IISc collaboration. We can try to make that as good, if not better. So I think we're really looking forward to the success of that proposal.
Same here, same here. Thank you, Professor. Thank you.
And I hope you have, on the lighter side, good soundproofing in your room, because your little one shouldn't have been wakened up by our voices. Anyway, should be used to yours.
She was awake at 3 already. She was like awake at 3, and we had a hard time trying to put her back to
Taken
bed.
after you. Right,
She was my
right,
alarm in a way to wake up.
Okay. Thank you so much, Ajay. We're just on time for the next talk, so we'll go ahead with that. It's all different links, so we will hang up with this.
Yeah. Okay, see you.
Thank you. Bye-bye.